thanks also to the organizers of this conference for putting together this nice program. As mentioned, my name is Leppert. I'm at the University of Twente in the Netherlands. And we are basically using first principles computational methods in order to understand excitons in a wide variety of halide perovskites. I want to also start by acknowledging the people who were involved in this work, in particular my former postdoc, Dr. Reza Joanna Biega, and collaborators Marina Philipp, Hema Karunadasa, and Jeff Neaton, as well as funding and computing resources as always. So we are particularly interested in perovskites because they basically provide us this large playing field of structures and chemistries, and we try to basically map out this electronic landscape that halide perovskites have as a function of varying basically chemical composition, but also dimensionality. So what you see here is basically an overview. Let me quickly see whether I can turn on my laser pointer. Yes. So what you see here is basically an overview of the structures that we've been interested in the last couple of years. What you see in A are basically the single perovskites that Filippo talked about in his talk. But in my talk, I will mostly focus on a class of perovskites known as double perovskites. So these are basically the structures you see here with alternating B and B' site ions. And then we've also been very interested in understanding excitons in layered perovskites lately, but because of the time restriction, I'm probably not going to talk about this. Yeah, and I really like this kind of picture of mapping perovskite electronic landscape or cartography of perovskites, because this is basically what the first explorers of perovskites did in the 19th century when the first halide perovskites were discovered. So double perovskites, the ones that I'm going to talk about, were discovered in 1885 in a place called El Paso County in Colorado, which you see here on this picture. The first report basically was a fluoride, I think, that was discovered by Cross and Hillebrand, and they were essentially just hiking around in these mountains, searching for new minerals and then analyzing them in the lab. And you can read about this in this Mineralogy of the Rocky Mountains, which is basically published by the Bulletin of the American Geological Society, and you can basically find this on the internet, and it's a very nice rabbit hole to disappear into if you have some time. And I always like to show this letter to the editor that Cross and Hillebrand were writing, where they basically say that this work was done by them in the office and laboratory at intervals of leisure from their regular duties during the past 3 years. So I think this must have been a very nice way of doing science back then. Anyway, so oops, I'm going back. No. So before we get to excitons and double perovskites, let me briefly recap what we know about single perovskites, their electronic structure, and also excitons in single perovskites. So when I say single perovskites, I'm basically referring to any halide perovskite with formula ABX3. So at the A side, we could have methylammonium, formamidinium, cesium, and at the B side, lead or tin. All of these materials have in common that they have a direct band gap that is usually also characterized by quite disperse band edges, which are close to parabolic and very isotropic. So the example that you see here is basically cesium lead chloride, but the band structure of other single perovskites such as methylammonium lead iodide also looks very, very similar. Excitons in these materials are very well described by the Vanier-Mott model, which is a textbook model, which you might have heard of, for excitons in semiconductors, where the exciton is basically described as an electron-hole pair, whose Coulomb interaction is screened by the dielectric constant of the semiconductor. And so we can calculate the the exciton fine structure or the exciton binding energy of this exciton by this hydrogenic formula, where we just basically have to solve the hydrogen Schrödinger equation, but replace the mass of the electron by a reduced effective mass of the electron hole pair. And then screen the Coulomb interaction by the dielectric constant of the semiconductor. So that's what we can do. Yeah, this is just telling you what the ingredients of this equation are. And this is very relevant for experimentalists as well, because when experimentalists extract exciton binding energies from, for example, absorption measurements, then they usually rely on the Wannier-Mott model as well. You can see this, for example, here. This is an linear absorption spectrum of methylammonium lead iodide measured in the group of Laura Hertz in Oxford. Where they basically used a so-called Elliott model fit in order to separate the contribution of excitons, so that's this blue line here, and the contribution of free carriers or free carrier transitions, that's this red line here. And this blue line is basically relying on a hydrogenic Rydberg series of excitons. So the functional form that's behind this fit relies on the Wannier-Mott model. And using this, you basically arrive at an exciton binding energy of around 16 millielectron volt for methylammonium lead iodide. Similarly, what can also be done is to measure optical absorption under large magnetic fields. So that's what you see here, basically, the absorption spectrum as a function of field strength. And then you can also basically distinguish the 2s peak, the 2s exciton peak here, and from the energy difference between the 1s and the 2s peak, you can also, using the Wannier-Mott model, extract the exciton binding energy. And this is basically from the group of Robin Nicholas, and also finding an exciton binding energy for methylammonium lead iodide of around 16 millielectron volt. So this is experimentally also very important to understand basically the character of excitons in halide perovskites and know whether you can use the Wannier-Mott model in order to extract exciton binding energies from measured spectra. And in fact, it turns out that for the single perovskites, one can also show from calculations that excitons are hydrogenic. So that means they do conform to the Wannier-Mott model in these systems. This is from calculations by Marina Philipp, who basically carried out very accurate calculations based on Green's function theory for the absorption spectrum of this is not methylammonium, I'm sorry, this is cesium lead chloride. And this is the calculation is basically the black line. And you see that it's in very good agreement with experiment, which are the dots. And then she basically also calculated the energy of the 1s and the 2s exciton, both from first principles. So that's what you have on the y-axis here, and compared it with the hydrogen model or the Wannier-Mott model on the x-axis. And you see that for all three of these halide perovskites, there's basically almost perfect agreement, both for the 1s and the 2s exciton. So the upshot of the story is that single ABX3 perovskites have hydrogenic or Wannier-Mott excitons. So our question was now basically, what is the effect of chemical and structural heterogeneity on excitons in perovskites? And as I said before, I'm mostly going to focus on the effect of chemical heterogeneity, which I basically define as the effect of having two different B sites in my perovskites. So what we do in our calculation is basically we always start with density functional theory. From that, we get structural properties, for example, but also we use this as a starting point for calculating electronic properties such as band structures. So what you see here is just a standard DFT band structure, including spin-orbit coupling self-consistently. But we know, as Filippo also said, that standard DFT tends to not be very good for electronic energy levels. And in particular, it underestimates the band gap of materials. And so what we do in the next step is basically to correct this DFT band structure using a Green's function-based method, which is called GW, or in our case, we use a flavor of this method, which is called G0, W0. And this basically gives us very accurate electronic properties. So we have quite accurate band gaps here and also more accurate effective masses, effective carrier masses than we would get from DFT. And then the last step is that we use the so-called Bieder-Salpeter equation approach, which is also a Green's function-based approach, in order to calculate transitions from the valence to the conduction band, but also take into account electron-hole interactions. And so by definition, this basically gives us information about excitons, but also about other optical properties. So for example, we can calculate absorption spectra. We looked at a variety of double perovskites. They all basically have the same A and the same X side. So they all have cesium at the A side and chloride at the X side, so that the only thing that we vary basically are the two metals that are alternating in this structure, so the B and the B dash side. And we compare the band structures and the optical absorption of these double perovskites with cesium lead chloride, which is basically our quintessential single perovskites with Vanya-Mod excitons. We think that these double perovskites are representative. They have very different types of band structures. So don't look into the details here. The point of this plot is basically just to show you that we have all sorts of different band structures here, direct and indirect band gaps, also different character of the band edges. So that affects the symmetry of transitions. And then, of course, also different band gaps. These types of band gaps and band structures, we already understand quite well based on a linear combination of atomic orbitals model, or if you're a physicist, tight binding. This is work we've done a while ago with Hema Karunadasa and her former PhD student, Adam Slavny, with whom we basically came up with a model that relies only on the frontier orbitals that are contributed by the B and B dash side metals, leading to a prediction at which K points you will find the valence band maximum and the conduction band minimum. So we have this nice table that allows us basically to predict, just by knowing what the two metal sites are, what type of band gap we can expect. And basically, the idea of looking at excitons in these representative double perovskites is to do something similar, to come up with a similar table also for excitons. So let's look into the details. So first of all, for these 7 double perovskites, we calculated the band gaps using the GW approach. So this is what you see here. So this is basically the right-hand side y-axis. And you see we basically span quite a large range of band gaps from around 1 electron volt up to more than 5 electron volt. Next thing that we do is to calculate the exciton binding energies. So this is shown here, and this is again calculated from first principles. So we get this from solving our Bieder-Salpeter equation. As you would expect from such a large range of band gaps, we also get a large range of exciton binding energies. You see we have some systems here that just have a couple of milli-electron volt binding energy, but we also have some systems that have almost 2 electron volt exciton binding energy, so almost molecular exciton binding energies here. What you also see at first glance is that the exciton binding energy does not necessarily scale with the size of the band gap. For example, one of the largest band gap material, the sodium-indium combination, does not have the largest exciton binding energy. And thirdly, if we are comparing now these exciton binding energies from first principles with those that we get from the Vanya-Mod model, you see that we have 2 types of systems here. We have some double perovskites for which the Vanya-Mod model works extremely well. For example, indium bismuth or silver indium, but also our sodium indium case here. And then we have other systems such as silver bismuth, silver antimony, sodium bismuth, and potassium bismuth, for which the Vanya-Mod model seems to terribly fail. We have really, really large deviations here. And the question is now why this is the case. And to answer this, I will pick out two examples that are kind of representative for the hydrogenic case. So this is one exciton that conforms to the Vanier-Mott model, indium bismuth. And here, the non-hydrogenic case, this is silver bismuth, which is also quite well studied experimentally. So to understand the specifics of these two cases, we basically have to question the two main assumptions of the Vanier-Mott model again. The first one is basically that we have isotropic and parabolic band extrema, so that we can, in this equation here, just replace an effective mass of the electron and hole. And this is very well true for indium bismuth and also for our other hydrogenic exciton materials, as you can see here. So this is basically plotting the conduction band minimum and the valence band maximum around the gamma point where the band gap is. And you see basically that in the longitudinal and the transversal directions, we almost have the same dispersion, so almost the same effective mass for indium bismuth, whereas for silver bismuth, we basically get very anisotropic effective masses or band structures. So we basically have one relatively low effective mass in the longitudinal direction, but in the transverse direction, we basically have relatively flat bands. And this is basically true for our other materials as well. We have hydrogenic materials which have a very low effective mass anisotropy, and non-hydrogenic excitons for the materials with very high effective mass anisotropy. The other assumption is a little bit harder to understand. So the other assumption is basically about the dielectric screening that we assume in our Vanier-Mott model. And for understanding this, we basically first need to understand how localized or delocalized the exciton wave function of these materials is. So what you see here is the excitonic wave function in reciprocal space. The dots are calculated from the Bieder-Salpeter equation, and the solid lines are basically calculated from the hydrogenic Vanier-Mott model. So this is basically just a 1s and a 2s hydrogenic wave function, but in reciprocal space. Okay, and we multiply it with 4 pi k squared so that you get something like an excitonic density if you want. So if you look at the x-axis here, you basically see this is in 1 over Bohr. So I can tell you that this is a very localized exciton in reciprocal space. So that means if you Fourier transform this into real space, this is going to be very, very delocalized.
Professor, 2 more minutes, please. Sorry to interrupt. Yeah.
No, that's fine. In silver bismuth, on the other hand, look particularly at the x-axis here. You see that we have a much more delocalized exciton. So that means if we go to real space again, this is going to be very, very localized. And you also see that the dots are not at all lying on these lines. So we also see here that our exciton is not very well described by the hydrogen model. We can calculate this exciton extent, and then we can connect it to the long-range behavior of the dielectric screening. So what you see here is basically the head of the dielectric matrix as a function of distance in reciprocal space. And you basically see this kx, this is our exciton extent, is basically very close to 0. So that means that the exciton here is just seeing the dielectric constant of the medium, of the semiconductor, whereas in silver bismuth, Kx is far more out here, so that the exciton sees much more of the long-range variation of the dielectric screening. And that's basically the second assumption of the Vanier-Mott model that breaks down in non-hydrogenic materials. And there is also a correlation of this for all of our other materials. So finally, that means we can actually come up with a table like the one before. Do not read it as it says here because it has too many details. The upshot of the story is basically that we can now map these anisotropies of the effective mass and the dielectric screening to the electronic structure of our double perovskites. This not only works for the systems that we studied here, but also for other types of perovskites, such as vacancy-ordered perovskites. And in conclusion, we basically see that halide perovskites really feature a very wide range of band structures in exciton binding energies that span several orders of magnitude. and that it's really the anisotropy of the electronic structure and dielectric screening, which are determined by the electronic structure of these systems, that determines the character of the exciton. And for experimentalists, I would say that the take-home message is that care should be taken when using the Wannier-Mott model for extracting exciton binding energies from experiment. And with that, I'm done, and I thank you very much for your attention.